Check. Okay, what's up everybody? Let's see, let me make sure the beat is working. Check it out on my phone real quick. Okay, there we go. All right, so I was actually doing something kind of fun yesterday. I was looking at the different JUCE components. Like I said, I use like the slider and combo box and button all the time. And I was looking at some of the other ones, thinking about which ones would be cool. And I wanted to do the progress bar, so I started to implement it. And when I implemented it, I also realized that I needed to have some simple multi-threading going on for it to work properly. So this is going to be a great tutorial because it's both progress bar and multi-threading in JUCE, which I kind of just figured out on my own. And JUCE has a thread object, so we don't even have to use the like standard template C++ or like C++ thread stuff. So let me show you what I got going on right here. Let me just build the app, and I'm not even doing a plugin, I'm doing a GUI app. So this is my little app. I've got a button that runs just this stupid little math loop to make it take a long time. Let me close it. So right here I've got my on click event for the button, and I'm running this thing that I made called progress operation. And that is just this for loop right here. I should say this for loop right here. It's just running just some random calculations, just something that I know, you know, takes a while. And then every time it runs, I'm keeping track of which count we're on and then turning that into a percentage, because the progress bar takes numbers between 0 and 1. So I'm just keeping a variable up to date on the current percentage. Obviously on the first run it's at 0 point whatever percent, and on the last run it's at 100%. So I don't have the progress bar in here yet. I just have an operation that takes a long time whenever I run it. So let me show you real quick. Whenever I hit this button, it's gonna run that loop. I'm running it like 500 million times or something like that, so that it takes a few seconds. And whenever it's done, you'll see done right here in the console. So let me click it right here. And you can see that since it's running in this on click event, the UI is locked and I can't even interact with this slider. So like the thread is just stuck on this one operation that's running. And it shouldn't run too much longer. Yeah, done. And now that it's done, I can interact with the UI again. So the UI is obviously running on a single thread, and whenever I click the button, we go into this progress operation, which is in here. And since this is taking, you know, 10 seconds or whatever, however long it took, the whole UI is locked for that 10 seconds in this button on click. So the only way to really rectify that is to move this operation onto a thread. But before we do that, let me put the progress bar in here. So the JUCE progress bar is pretty simple. It's only got a couple of public member functions. It also doesn't have a default constructor. You can see that it expects something in terms of parameters to build it. So let me see. So if we want to make one, I could say JUCE ProgressBar. And then I think I'll just call it meter. And if we just do that and we hit build, it'll tell us that we didn't fulfill the needs of the constructor. It says constructor must explicitly initialize the member meter because it doesn't have a default constructor. So one thing we could do is we're going to use this current percentage with the meter anyway. So I could pass that in right here in brackets, and that would work for sure. Yeah, so that built. So that's good. We could also, if we didn't want to do this, we could go into the constructor of the CPP file right here. Oh wait, no. Yeah, no, we can't do it like that. Sorry. The other way we could do this, I'm going to copy this JUCE ProgressBar. We can use a smart pointer. So we've done that before. It's that STD unique pointer and make unique. So we could do that. Unique pointer. And this is really useful for if you have a class that requires some kind of variable that so this is really useful for if you have a class that you need to create an instance of, you know, at startup like this at initialization, but you don't have access to this variable yet. If you make it a unique pointer, you can go and construct it later, and that's what I'm gonna do. So I'm gonna go right here and say meter is equal to, and just like the parameter attachments, it's going to be std make unique. I'm going to paste the progress bar, and then we can give it the variable for the constructor. So was it current percentage? Yeah. And the only annoying thing is now that this is a pointer, whenever we do things like add and make visible, so we're actually going to have to say meter.get instead of just passing in meter, because meter is a pointer. And then also if we call any member functions on it, so for example, set percentage, set text to display, or set bounds, instead of using a dot, we're going to use an arrow. So I'll show you right here. And I have, you can see set bounds as an option. Since it's a pointer, we're using this arrow operator. And I already have this figured out. I have it written down. Let me just pull and copy that. Let's see here. That. I'm gonna get rid of this and paste that stuff in, and let's see what happens. Make sure it comes up on the screen. Yeah, so here's the progress bar, and it is currently, or let me go to the documentation. The documentation actually tells you that you pass in a reference to a double that you're going to update with whatever you're using to update, you know, that thing. And progress bar automatically monitors the value of this variable and redraws itself when the value changes. So it's kind of already listening for you. So let's run it and see what happens. Well, it's running right now, so let's restart it. So right now it says 0. I'm gonna hit engage, and it's running our function. We don't really see the progress bar moving. We can't move this slider because the UI is locked on that single thread. And when it's done, the progress bar shows 100%, but we didn't get the actual progress. And that's because it's on a single thread. So this function right now is running, and the progress bar isn't able to write or isn't able to update itself because the thread is currently stuck on this. So we need to move this to another thread, and we can actually do that pretty easily in JUCE. So JUCE has its own thread object, but it is, I'm pretty sure it's an abstract class. So we're gonna have to actually just create a class and inherit from it. So we can create a meter class. I'm gonna call it, I'm just gonna put it here in private, by the way. It doesn't really matter for this small example, but but yeah, it'll work. So make a class, I'll call it meter thread, and it's gonna inherit from a public JUCE thread. Okay, the class, so semicolon, and in public we have to implement, I mean, it doesn't have to be public, but we have to implement its run method. So, but before that, we also need to give it a constructor. So meter thread JUCE thread, and then give it something, a name. And yeah, curly brackets. Let me do this. So there's the constructor, so that should take care of that. And we need the run function, the actual thing that the thread is gonna do. So it's an override function, so we just do it like this: void run override, and then yeah, we'll just implement it, and then this will be do something. And the easiest thing is I'm just gonna take all of this stuff right here that's doing our progress, and I'm just gonna stick it in there just for the ease of use. Yeah, and then in override, or in run, we're gonna run this progress operation with run length, and I had to put it up to like 500 million for it to take, you know, long enough to actually make it a good example. So yeah, so we're gonna call progress operation in the thread. So now this new thread is handling it, and we're gonna go back into this button on click, and instead of running that, we're gonna say, oh, we need to make an instance of our class that we just made, meter thread. Meter thread. So now we have an object. Now we have an instance of this class. So we can go into here, and on click, we're gonna say meter thread dot run, and that will run whatever is in this run method that we implemented, this virtual method. And this is gonna run on another thread. We also need right here, now it doesn't know what current percentage is because it's in meter thread. So we could just say meter thread dot current percentage. That should be good, right? Yeah, that's good. And then let's check out a couple other things with thread. So let's go to JUCE docs. I'm gonna go to thread. And besides creating an instance, so we have start thread and we have stop thread, which is pretty important. This one is also really important. Signal thread should exit. This is like a way to force the thread to tell it to stop. So I'm gonna actually use that whenever it's done running this. So progress operation is gonna run for a few seconds, right? So whenever that's done, I'm gonna say signal. I'm gonna have to type some more, I guess. Yeah, signal thread should exit. So we'll put that there, which will tell the thread not to keep running after we're done with our, you know, our operation right here. And we can go ahead in the destructor. Probably be a good idea to also say stop thread, meter thread dot stop thread. Oh yeah, and it gives it a timeout. So Stop thread. Attempts to stop the thread running. Hopefully the thread will then respond to this by exiting cleanly, and the stop thread method will wait for a given time period for this to happen. If the thread is stuck and fails to respond after the timeout, it gets forcibly killed, which is a very bad thing to happen, as it could still be holding locks, etc., which are needed by other parts of your program. In our case, I don't think that's really an issue. But if you were running, or if you were building a large application that was complicated, that would probably be an issue. So I don't know. I'm just gonna put a second. So there we go. Stop thread in the destructor. Just kind of doing some cleaning up after ourselves. And I guess we're ready to try this. So let's review. We've got a progress bar object, and I put it on the window. It's watching this current percentage, which is being tracked in this loop. And this loop takes like, 6, 7, 8 seconds, something like that. And when we click the button, the thread that we created, we're telling the thread to run. So what should happen is, or what was happening before was button on click. We click the button, it's doing this operation, but the operation took 6 seconds. So for 6 seconds, we were stuck right here and the program wasn't going anywhere. So now we're gonna click the button, we're gonna say start a new thread. And since that thread will be separate from the one that we're on, execution this direction will keep going, so the button won't be locked and the UI won't be locked while the thread is running. So let's try that and make sure it works. Okay, go. Ooh, I missed something. Okay, weird. Meter thread. Let me check my notes. Let's see. What did I do wrong? Meter thread, progress operation. Signal thread should exit. Meter thread dot run. And signal thread should exit. Okay, live debugging. Okay, so what am I missing? Thread meter thread. Thread dot run. Percentage. Run count, new run length. What's wrong? Okay. Oh, wait. Is it start thread? Yeah, it's okay. Yeah, that was all it was. It's not run, it's start thread. I was calling run, which is just holding the operation. Yeah, okay, so let's turn this off. Apparently it's really slow. So I'm gonna go in and I'm going to make it a little quicker. So let's take 1.0 off. And let's see how fast that is. Still slow. That's way too fast. That's better. Okay, that's a good speed. Okay, so it's done. Okay, so the issue was, I don't know why I was doing that, but I was calling run, which run is only calling the process. It's not actually, you know, starting the thread on a new thread. So this is the whole point. So we're calling start thread, which will automatically call the run for us and it'll do everything. So check this out. We're going to start up the app. We're going to engage and the progress bar is actually going and we can move this fader, which means that the main UI thread isn't stuck. And we can see that whenever it was done, it printed out done. And we can do this over and over again. Yeah, and then whenever it's done, we're just calling signal thread should exit. And that's pretty much it. I'm sure there might be a little bit more involved in making sure that the thread stops cleanly. Because we have a couple of different methods. We've got stop thread, signal thread should exit. Oh, this is cool. There's also a wait. Suspends the execution of the thread until either the specified amount of time has elapsed or another thread calls notify. Oh, and then notify is cool because you can wake up the thread and then you can set priority, changes the thread's priority. That's pretty cool. I don't know when I would ever use these, but it's cool to have, and it's cool to know that you can use a JUCE thread instead of a C++ thread, which, you know, come on. So yeah, that's the progress bar and basic multi-threading in JUCE. So another thing I wanted to do, I think, was I want to try to speed up the execution of polynomials, because I've noticed that those take a long time in the code. Definitely, if I'm doing distortion, I'm using a polynomial. It definitely uses way more CPU. So I have another, let me open up a different project. I have a console app project that is nice and simple, just to test the timing of things. Let's see if it's in my recent, let's see. Wait, progress bar, what's thread? Oh, this is an actual C++ threading exercise that I did using the standard template library and mutexes, locking and unlocking. I have a simple little console app. I keep forgetting, is it on the desktop? Skyscraper that already has the stuff in it. Nope. Skyscraper rectangle, let's see here. No, I need the one that has timing stuff in it. CPP test, let's see. This one have any kind of timing? Nope, that's just a basic one. I refuse to copy and paste the code. Oh, that's not. Yeah, that's that phase stuff I was doing. I'm gonna find this project because I refuse to copy and paste this STD chrono stuff that I don't feel like doing. ESP test? Yeah. Okay. There it is. So what this is doing, this is kind of convoluted looking. So this right here, let's check this block out. So this block, we're starting a timer. I'm running a method. I'm stopping the timer. I'm stopping the timer. And then I'm saying that this operation took this amount of time. So the timer time that you get is the timer time that you get is automatically in microseconds. So you got to multiply it by, you know, this dumb number to get your seconds. And then I'm just keeping track of how many seconds that took. And then I'm doing a second method, the same thing, just with a different method, but I'm also timing it and saying how long it took. And then whichever one takes the least amount of time, I'm just printing out to the console, this one was faster than this one by this amount. So let me just show you how it looks. I basically have two methods called phase conditional and phase expression, and I'm just seeing how long each one takes to run. And it's just a console app, so it's really easy. I just have a main method. Let's see here. It's gonna say something eventually, I think. The phase conditional took 11 seconds to execute. So apparently I'm doing it a bunch of times. So we're gonna have to sit here for another 11 seconds. So it timed how long the first two methods took. It tells you which one was faster and by how much. So I want to do that. And I want to create a function called polynomial. And I'm just going to say double x is equal to 0.5 or something to represent our audio signal. I don't feel like seeing the red arrows, so I'm just going to put polynomial in here. And then let's do some kind of dumb polynomial thing. So let's do double y is equal to, let's say, 10 times pow of x raised to, I don't know, 3. Okay, plus maybe like 16 times x raised to like 5, and then we'll do like 9 or something. Minus 20. Times that raised to the 9. 369 and that. Okay. So that. Oh, and then let's use y. So let's do something that's slow. So let's divide it by 2. Cool. And let's make a for loop so that it runs a bunch of times. We'll say int 0, or sorry, int I is equal to 0. I less than 1,000. I plus plus. And I will just bury this inside of 3 for loops. Oop, accidentally. Oh. What was that all about? That was crazy. being weird. Okay. So we're going to bury it into 3 for loops so that, you know, takes a long time. A long time, relatively speaking. So let's see how long this takes running 1,000, 1,000, then 1,000. Longer than I thought. Let's make each one 100. Wow. Okay, so that was way faster. I'm just looking for like, yeah, something like 3 seconds or something. Okay. So this is going to be the STD PAL, because the whole thing I want to do is I want to optimize my PAL function instead of using STD PAL. I found something on Stack Overflow, or I don't remember, you know, one of those forums. Somebody posted a code snippet that does this, what the PAL function does, but faster. So let's say the STD PAL took this amount of time, and then we'll say the optimized PAL. So we'll say, make 2 different versions of this. So we'll say STD PAL and then optimized PAL. And we'll say STD PAL here and optimized PAL here. Okay, and I'm gonna just need to make another function that's gonna be the optimized PAL function, which now doesn't make sense because I already have optimized PAL. Let me call this something else maybe. Slow version and fast version. And then I'll make a function called void optimize PAL. Guess it's actually going to return something, but yeah, let's see. I took a screenshot on my phone, but it might be better just to go online and find it. So let's say optimize C++ std PAL. What is more efficient using? Oh, then they're saying just not using PAL at all and just actually multiplying the number by itself is actually faster. Okay, this isn't the right post. Let me look at my phone. Trying to think of what I Googled. I might have said something like C++ fast PAL. Oh, this is it. Yeah, this is it right here. So it relies on type punning through a union, which is undefined behavior in C++ from the draft standards section. In a union, at most one of the non-static data members may be active at any time. That is, the value of at most one of the non-static data members can be stored in a union. But most compilers, the practice of reading from a different union member than the one most recently written to is common. Okay. Oh, but this is not universal. He says. But anyway, let's try it. So inline, I'm just gonna get rid of that and say fast pal. I cannot stand the first bracket being on the same line. It's so ugly. Oh. Okay. Okay, cool. Fast pal uses a union, apparently. This is wild. Let's see if it's any faster. Okay, so this is supposed to be the fast version. So we're gonna say fast. So this is gonna be 9, 6, 3. It's gonna be X. Okay, I think that's it. Use of undeclared identifier. Fast pal. Okay. Slow version, fast version. All right, let's see if it's any different. Oh, it was very different. Let's do it again. 62% faster. Oh, 67. It's almost, I mean, it's more than 1.5 times faster. %72% faster. Okay, wow. Okay, so let's do another one. And I want to try doing, oh, that's not what I want. Fast version 2. So instead of using fast pal, I'm just gonna say X times X times X. I mean, this looks really stupid, but if it's even faster, I'm down. So that's 6. That's 9, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. Yep. So that's fast version 2. Okay, so let's do fast version, or let's do fast version 2 to see if it's actually faster than the original slow version. I think. Oh my god, look how much faster. Just using... Oh, but this isn't going to be possible in the DSP polynomial, right? Because I'll have our input. No, this will work. Yeah, because X is my input, so I could say XXX. Yeah. It looks really dumb, but it's so much faster. I wonder... So obviously we're doing this in debug. So let's build it release and see, because maybe in a release build, the compiler might just optimize it to where they all do the same exact thing. So we'll close that and let's build. And then we can tell if this is a release build or a... Oh no, we can't, because I'm using... Yeah, I'm not using debug, I'm using stdc out. So let's go into the folder, which this is, yep, DSP test, Mac OS, build, release. Let's run that. Oh. The std pal took 0 seconds to execute. Okay. Oh, you know what? I bet it's in release mode, so it's running so fast. Let's do it like that. 5,000. It's still really fast. Oh, wait. I gotta put the same number here. Okay. Fast version 2. Build. Something's not right. Interesting. I mean, it's not optimization, right? There's no way it's that much more optimized where I can put... Something's not right. That's weird. Something about it being release mode. I mean, I have no idea what that might be. Oh, probably, yeah. I'm gonna go back to debug mode. And let's take this back to 500. Let me just make sure, let me just build and make sure it works correctly. Oh. Scheme, edit scheme, executable, DSP test, close. And then if I hit the play button or run. Yes, okay. So let's see. So let's print the result. So after the for loop, we'll say the how result is y std indel. Okay, so that, and then we'll say this. The PAL, no, this is the, I don't know, I'm just gonna call it direct or something. Huh. Is that gonna be enough? Let's see what happens. Oh, they're getting different. Yeah, they're getting different numbers. Let's, what would be the best way to see what the actual answer is? I don't know how to do this on this calculator, but I'm just gonna. I'm gonna assume this calculator was coded by somebody better than me, so I'm gonna see what the answer looks like. What? What? Is that correct? Wait. Let me get rid of this. Oh, yeah, I didn't. Okay, yeah, I just need to do 1.71094 85547. So it looks like, I don't know if this is the best way to tell, but it looks like this one is more accurate. That seems like a big difference though, from 0.83 to 0.85. I think, would floats be worse? No, it looks about the same. Stacking, multiplication, you mean this? This part right here? Yeah. So if I say, yeah, that makes sense. Yeah, let's see the difference between STD PAL and fast PAL. What is it? Slow version and fast PAL. Wait. Slow version 500. Okay. And fast version also 500. Okay. Let's see the difference between the STD PAL and then the one that's supposed to be an upgrade to STD PAL. Oh, I didn't put the result in. Let's see the. Okay, so let's say the PAL result. The PAL result, the fast PAL result. Okay. And that should be good. Pilot wouldn't optimize it because it cannot assume you're okay with the precision loss. Okay. Yeah. Oh wait, am I still running the wrong one? I'm still running the wrong one somehow. Oh, fast version 2. Now this should be correct. Oh, it's very different. The power result is 0.73. The fast power result is 0.83. But then the question is, oh, let me just make sure that nothing's incorrect. 10 raised to the 3, to 16, raised to the 6, minus 20, raised to the 9. Yeah, so the results are very different. But the thing is, this is supposed to be a distortion algorithm, so the important part is that it runs fast, not the right values, or not that the precision is 100% correct, right? I mean, the idea is to make it faster, and it's distortion, so however it sounds, you know, it's cool, whatever. Let me go into here. So I'll go into, oh, let me put my modules in here. So, oh, you know what? I bet it won't let me. It says the DSP module isn't there. Oh, okay, because DSP relied on something else. Okay. So let's put mine in here. And we'll go Vitor DSP modules. Open. Okay. Use modules, Vitor modules. We'll go into utils and let's see. Inline function, fast pal. Vitor utils. I'm just going to put this down here. I guess I'll say static. Double fast pal. Should I call it something else? Fast pal is probably okay. Let's see if I can go and actually use it. Let's see, fast version. It's gonna be fast pal. Okay, so we're gonna say Vitor utils fast pal and X in 3. And then 6 and 9. Let's make sure it actually runs. Oh, it's gonna be all the, yeah, all the stuff in my modules that probably relies on something that this this project type doesn't have. But it let me do it, so I'm gonna assume that it's okay. So let's go maybe I might be able to use it in the other app. Let's see. Let's see if it'll let me do it right here. Is this gonna run? Oh, it's gonna work. Ooh, it works. Okay. Okay, so we know it works in this project. So let me clean it up a little bit. Tour modules. I'm kind of thinking now it makes sense to expand the utils namespace to be utils. Let's say struct utils. Okay, so okay, now we've got a struct called fast math, and if I do any more, I'll put them in here. And that means we go back here, and instead of utils, it should be fast math. Look at that, it works. And our threading still works, which is cool. This was a really fun project to work through yesterday. It feels good being able to do something multi-threaded for some reason. Okay, let's see, anything else? Let me go ahead and say added fast math name space in utils. And let's go back. How much faster was this? Utils, fast math. Oh, wait, I'm stupid. I can't do that. We just went through this. Okay. And we're still using slow version, fast version. So how much faster was it? Wait, I'm still getting errors. Oh, I gotta take out the modules. Okay. DSP test. Let's take out module. Okay. Let's build it. That's a lot faster, 45%. Because I was getting results that were like 70% faster. Let's make it take a even longer amount of time. See if that makes a percentage difference. Wow, it's taking a lot longer. 17 seconds. It felt like 10 minutes. %. Okay, so let's make it a lot faster. So let's make it 100 times. I know what you're thinking. If this was a global variable, I could just change that global variable. So the same percentage. So even if it runs really quick, it's still much faster than the quote unquote slow version. So let's make it really fast. Oh, at really quick intervals, it seems to be even faster. So that makes me think that at the audio rate, it's going to be a whole lot better. Yeah. So for example, we could say it's going to be, we can take one of the inner for loops out. And we could say two for this one, because this would be like our channel sample loop. So we'll say 2, and then this one, worst case scenario, you know, 1024. So let's take that slow version, fast version. So now this would better represent what's happening at the audio level, which I think is really fast. So let's see. Okay, so 50% faster. Oh, that was 9% faster. 32% faster. 44. Okay, so it's very inconsistent, but it seems to be faster. Almost 4 times faster that time. Wow. Okay, so that's good to know. I implemented that fast version. Yeah, I don't know about the precision loss. I mean, what if I... Wait a minute. Let's make sure I get the same result if we run std_pal twice, which I'm assuming... Oh, wait a minute. Wait, I'm running... Oh. I've been running std_pal twice. Was I getting the same result? Yeah, getting the same result. Okay. So I wasn't even running the different... Okay. I am so dumb. Fast pal. Okay. Now. Okay. That precision loss is crazy though. From 0.73 to 0.83. But it's way faster. And it's off by the same, is it the same amount each time? Yeah, it's the same. It's the same number each time. Yep. Too bad I didn't see your message. I wasn't calling fast. I wasn't calling fast pal the whole time. I was getting the same result and not even realizing it. Yeah, I know I can afford it. It's just that on this distortion, I'm using it for a distortion algorithm. So if using this fast pal makes a difference in CPU, that would be good, because I might use this polynomial SCD pal a lot, like in a overdrive and an amp sim. So an amp sim is going to be using a lot of CPU because of the impulse response convolution and filters also. So if I can save, if it makes enough of a difference, like we could test it in logic and see how much CPU is using, and if it's using less CPU and like significantly less, then I'll be happy with it. Because like I said, it's going to go into an amp sim, so any little bit of CPU that I could save would be good. It might not make that much a difference even in a release build, so I'm not really sure. But JUCE has a built-in, there's a class called Fast Math Approximations that doesn't have PAL, but it has like, what does it have? Oh, cosine, sine, tan, yeah. So it doesn't have PAL. And I've used this before for like tan, especially for tan. And there's another one. So this is in DSP, and there's another one called Math Constants. Oh, that's not, yeah, whatever. Yeah, you get pi, 2 pi, half pi, whatever. Yeah, so since this fast math exists, I assume that it makes enough of a CPU difference to matter. So I'm gonna have to try it out in a distortion algorithm and see if it does anything. Yeah, if your audio ranges from -1 to 1.1 is a ton of precision loss. You're right. I wonder if there's something that we could do to make this better. Oh, this is where the precision loss is happening, where it's being cast to a int right here, I bet. Okay, there were some other things on, looks like Martin. Replace all of your values with their logarithms instead. Multiplication becomes addition. Division becomes subtraction, and exponentation becomes multiplication. But now addition and subtraction become expensive and somewhat error prone. This is saying using POW is overkill and using just like x times x. If the integers are small but not known at compile time, say between -12 and 12, multiplication will still beat POW and won't lose accuracy. You don't need 11 multiplications to compute x to the 12. 4 will do. Use the fact that, yeah, blah, blah, blah. Okay, that makes sense. So let's just do this. Okay, 3, 6, 9. So I think what it's saying for this one, we already say x times x times x is to the third. So what we can do, I think, for this one, for 9, is that right? X to the third times x, does that equal x to the 9th? Am I dumb? So 3 to the third is equal to 27. Oh wait, no. I need to know 3 to the 9th, which is 19, whatever. So 3 to the times 3. No, I am completely wrong. That's not how that works. Times 3 to the 3. Okay, I'm dumb. One, 2, 3, 4, 5, 6, 7, 8, 9. Let me read this again. You don't need to 11 multiplications to compute x to the 12. 4 will do. Use the fact that x raised to 2n is equal to x raised to n raised to 2. For example, x to 12 is xxx times 2 times 2. Okay, whatever. Fast version 2. Okay, so we know slow version is giving us the correct answer. So let's see if this dumb looking multiplication gives us the same result, but is faster. The result is way different. Or what if we did this? Wait, let me think for a second. So make sure slow version is definitely using PAL, right? Okay. Oh, well, I mean, I don't have enough X's in that one. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. So I was missing one term here. Okay, so they're getting the same value. Oh, but look how much faster it is. Oh my God. Okay, well, there we go. It's 564,000 times faster. That might not be the case in a release build, but also... Oh, wait, hold up. I don't have the same setup. That's why. I'm gonna copy this. I'm gonna put that in fast version. Because, you know, the for loop setup was different. So let's do fast version. Now this should be correct. Now they're running at the same amount of times. The expression version was faster. Oh. I think it was correct, but I do want to change this. Direct. The direct version was faster by 550%. 830%. Yeah, it took me a second to figure out, but yeah, the loops were different. So at this level, we're looping twice to, what am I trying to say? So we're trying to make the same DSP loop. So I'm doing one for loop twice for, you know, your channel loop, and then another for loop 1024 for like your sample size. So this really isn't a lot. So we're only running 2048 times, which is very simple and easy. So I wonder if, and I'm thinking because it's so easy for the computer to do this fast, that might be why the percentage of how much faster it is wildly different each time. So it might be possible that running it a bunch more times makes it a little more consistent. It still didn't take long to do. 360%. Yeah, it's still really fast. Mean IJK. Okay, so this is taking like almost 2 seconds. So 273%, 278%, 289. Okay, yeah, so like I thought, the more times it runs, the more consistently, or the more consistent the percentage is of how much faster it is. So far, at least. Maybe not. Maybe I might be wrong. It's still, the first like 3 or 4 looked like they were consistent, but now it's starting to change. Okay, so the consistency in that it's faster seems to be true, just not how much faster. And go back to 2. %, 560, 390. But at least the results are the same, so yeah, that fast math one, the results are just too wildly different. So let me go back to using the fast math one. So let's take this, put it in this one, and we'll use FastPow. And make sure we go to 2. Man, look how different the answer is. And I'm assuming that precision loss happens right here, where this term right here gets cast to an int. I mean, does it make a difference if I... What happens if... Let me... Let's do a static cast and see if it makes a difference. No, it's the same number, so it doesn't really matter. But do we need to cast it to an integer? Nah, we get the same thing, it doesn't matter. Oh well. Well, this has been an interesting night. I feel like I've learned a lot. I guess I'll just have to try it in the context of distortion and see if that precision loss is that much of a bad thing for distortion. Because the whole point of a like polynomial distortion is to like really heavily distort, you know, use it as an overdrive or like an amp distortion. So I don't know, the precision loss might not be an issue, or it might be a huge issue, I don't know, but I'll try it out and see. But I did have a lot of fun doing the threading with the progress bar. Let me pull that up again real quick. Just, I think maybe everybody who's in the chat. Oh, they're all gone. Never mind. Progress bar. Let me just open it real quick. So to go over what we did, I made a progress bar and called it meter. And I made a stupid method right here called progress operation that is just doing this dumb math just to make it take time. And we're keeping track of the percentage done each loop to send that to the meter. But we were calling that on the button click, and it was locking the UI. So we had to move it to a thread. So on button click, I created a thread class called meter thread, which inherits from JUCE thread. And I'm calling this dumb progress operation in here, and then making sure that the thread exits after it's done. And then we're starting that new thread on the button click so that we build it real quick. Yeah, so when I hit the button, the progress bar moves around, and while the progress bar and that method is calculating, I can still interact with the UI without it being locked, which is good. Because if I take this out and just do meter thread dot progress operation, I guess I have to say meter thread dot run length. Now it's not going to be on another thread, and we're just going to run that operation method whenever I click the button. And since the UI is on one thread, oh well, it ran really fast, but So the UI is locked. I can't do anything because the UI is on a single thread and it's still in that on click event while it's running that method. So you can see that we can't do anything. The progress bar isn't going up. But whenever it finally finishes, which might be a while, I don't know how much faster or how much slower I made it. But once this finishes, the progress will show 100. Yeah, it shows 100 and then the UI isn't locked anymore. So that's why I moved it to a thread. Take 1 0 out, make it a little slower. And yeah, there we go. We got a progress bar moving. I could still use the UI because it isn't locked on one thread. And it's going. That's pretty much it. That was a lot of fun to do. I'm glad that I figured that out. That might come in handy at some point. Yeah, I think I'm going to cut it right there for tonight. Thanks for watching, everybody. I will definitely turn this into some better edited clips on YouTube, so that maybe I'll have like a 10-minute video going over this whole multi-threaded example. And then I'll probably make a video out of this testing the well, not this, but you know, the last project we were on, testing the speed of the POW and stuff. That's going to take a lot of editing because that was a lot of trial and error. But yeah, thanks for watching. I'll be back Monday. Feel free to keep being active in the Discord.